Hey guys, Lainey here, and today I'll be walking you through my thought process of Danny's challenge. This problem focuses on evaluating settlement of a footing supported by a thick layer of compacted structural fill. First, I'll go over the problem background. We are evaluating settlement issues for a site with 25 feet of compacted structural fill over native soil. The fill area is relatively large at 120 feet by 125 feet, which is important later when we consider influence area assumptions. The groundwater table is located 25 feet below grade, and the footing being analyzed is a 7 by 7 foot by 2 foot thick isolated footing. The applied column load is 127.5 kips, and the top of footing is located 1.33 feet below the finished floor. The general soil profile was provided to us for this challenge and outlines the soil layers present at the site, along with their corresponding depths and soil classifications. For this analysis, we focus on the top 3 soil layers, as these layers fall within the zone of influence for the applied fill and footing loads that are included in the settlement evaluation. The unit weights, initial void ratios, compression indices, recompression indices, and pre-consolidation pressures associated with these layers are used throughout the consolidation calculations. This soil profile establishes the framework and assumptions for the settlement analysis that follows. The first step was evaluating the influence area of the fill. The ratio of planned dimension to depth is 125 feet divided by 35 feet, which gives a value of approximately 3.6. Since this ratio is several times larger than the depth of the compressible layer, we can reasonably assume vertical stress distribution and one-dimensional consolidation behavior for the deeper layers. In order to determine the initial vertical effective stress in layer 2, we need to use the mid-depth of the layer, which is where a depth of 10 feet comes from. Since this layer is located within the groundwater table, it is important to subtract the pore water pressure because only the effective stress carried by the soil skeleton contributes to consolidation behavior. The pore water pressure does not contribute to soil compression, so it must be removed from the total vertical stress when calculating the initial effective stress. Based on this calculation, the initial vertical effective stress in layer 2 was determined to be 0.326 kips per square foot. Now that we have determined the initial effective stress in layer 2, the next step is to determine the additional stress in this layer caused by placing 25 feet of structural fill on top of it. Since the structural fill is located above the groundwater table, the full unit weight of the fill contributes to the increase in vertical effective stress. Therefore, the stress increase can be calculated by multiplying the soil unit weight of the fill by the total thickness of the fill, resulting in an added stress of 2.75 kips per square foot. Adding this stress increase to the initial effective stress calculated on the previous slide results in a total effective vertical stress of 3.076 kips per square foot, acting on layer 2. In order to determine whether layer 2 is experiencing recompression or virgin compression, we need to compare the effective stresses to the pre-consolidation pressure provided in the table. The initial effective stress is below the pre-consolidation pressure, which indicates that the soil is initially in recompression. However, after accounting for the additional stresses from the structural fill, the final effective stress becomes greater than the pre-consolidation pressure. This means that as loading increases, the soil in layer 2 transitions from recompression into virgin compression. Using the values provided in the soil parameters table, along with the initial and final effective stresses determined in the previous slides, I calculated the primary consolidation settlement due to the fill loading. For layer 2, the resulting settlement is 0.65 feet, or 7.8 inches, which well exceeds the allowable displacement and would need to be addressed in the design. To evaluate the settlement caused by the footing, we first need to determine the net pressure at the base of the footing. This net pressure includes the applied column load and the self-weight of the footing. However, it is important to subtract the weight of the soil that was removed to construct the footing. This is because the soil originally occupying that space was already contributing stress to the ground, and replacing it with the footing does not represent a full additional load. By removing the weight of the excavated soil, we isolate only the new stress introduced by the footing system. Using this approach, the resulting net pressure at the footing base is calculated to be 2.68 kips per square foot. To determine the vertical stress increase in layers 2 and 3 caused by the footing loads, I evaluated the stress distribution using the Westgard influence area chart. For both layer 2 and 3, the calculated Z/B ratios exceeded 4, which indicates that the stress increase from the footing dissipates significantly with the depth. At these ratios, the additional stress contribution from the footing becomes negligible. As a result, layers 2 and 3 do not experience meaningful additional settlement from the footing load, and only layer 1 contributes to settlement due to the footing. To determine the stress increase within layer 1 caused by the footing load, the layer was divided into 4 equal sublayers labeled 1A through 1D. Each sublayer is evaluated at its mid-depth to determine the appropriate stress influence factor. For layer 1A, the midpoint is located at a depth of 1.75 feet, which gives a Z/B ratio of 0.25. Using the Westergaard influence chart, this corresponds to an influence factor of 0.7. For layer 1B, evaluated at a depth of 5.25 feet, the Z/B ratio is 0.75, resulting in an influence factor of 0.32. For layer 1Z, the midpoint depth is 8.75 feet, producing a Z/B ratio of 1.25 and an associated influence factor of 0.15. Finally, layer 1D is evaluated at a depth of 12.25 feet with a Z/B ratio of 1.75 and an influence factor of 0.09. Using the net footing pressure along with the influence factors determined for each sublayer, I calculated the vertical stress increase within layer 1. As expected, the stress contribution from the footing gradually decreases with depth, since the applied load dissipates as it spreads through the soil. The calculated stress increases range from a maximum of 1.876 KSF in the uppermost sublayer to 0.241 KSF in the lowest sublayer. When combined, these values result in a total stress increase of 3.377 KSF across layer 1. Based on the stress distribution results from the footing load, layers 2 and 3 experience negligible additional stress. As a result, these layers remain in recompression under the applied footing loading. Layer 1, however, is significantly influenced by the footing stresses. The increase in effective stress within this layer exceeds the pre-consolidation pressure, placing layer 1 in virgin compression. Because of this, the primary consolidation settlement associated with the footing load must be evaluated for layer 1. Since layer 1 was determined to be in virgin compression due to the footing load, the next step is to calculate the additional primary consolidation settlement for this layer. Layer 1 was divided into 4 sublayers, each with a thickness of 3.5 feet, to account for the variation in stress with depth. Beyond a depth of approximately 14 feet, the additional stress from the footing becomes negligible due to the stress dissipation. Therefore, soil below this depth does not contribute to settlement from the footing load. The calculated settlements for each sublayer are layer 1A contributing 0.39 inches, layer 1B contributing 0.3 inches, layer 1C contributing 0.21 inches, and layer 1D contributing 0.12 inches. When these values are combined, the total settlement for layer 1 due to the footing load is 1.02 inches. When compared to the 7.8 inches of settlement caused by the structural fill, this indicates that the primary driver of settlement concerns is the addition of the fill rather than the footing itself. Adding both contributions together results in a total estimated settlement of 8.82 inches. Up to this point, the analysis has focused on the magnitude of the settlement, but it is also important to consider how long the settlement will take to occur. To evaluate this, I analyzed the time rate of primary consolidation using Tergazzi's one-dimensional consolidation theory. The time required for consolidation depends heavily on the drainage conditions within the soil. For this problem, both one-way drainage and two-way drainage conditions were evaluated to capture the possible range of settlement times. Under one-way drainage, consolidation can occur in a single direction, resulting in a longer drainage path and slower dissipation of excess pore water pressure. Using this condition, the time required to reach 90% consolidation was calculated to be approximately 3 years and 35 days. Under two-way drainage, Consolidation occurs in both directions, which significantly shortens the drainage path. In this case, the time to reach 90% consolidation was reduced to approximately 283 days. This comparison demonstrates that while the total settlement magnitude remains the same, the rate at which settlement occurs can vary significantly, ranging from several months to several years depending on the drainage conditions. Thank you for following along as I discussed my thought process and approach to evaluating settlement for Danny's challenge.